Thank you for joining us today, Grace.
Thank you, Michelle, and I'd like to welcome everyone here who's on the line listening to our presentation today, our webinar on using microwave technology for peptide synthesis. I hope we can have a good afternoon today and have some good information for everyone. So what I want to do here to start off is I just want to ask a quick question of everyone who's here with us. My first question is, do you currently use a microwave system to perform your peptide synthesis? So you've got a couple options here. Your first option is, yes, I use a CEM instrument. So this would be perhaps one of our peptide synthesizer or Liberty systems. Another option is you use another vendor's instrument. I will not hold that against you, but just curious if you do. You might perhaps be using a conventional synthesizer, so say you've got one of those old ABI systems that's still limping along, or you might just not be doing peptide synthesis yet, but you're looking to get into that, and so you're looking to get some more information. So just let us know, using a CEM system, another vendor's conventional synthesizer, or you're currently not doing peptide synthesis. So I'll give you a few more seconds to get your answer in, and then we'll tally the results. So how about 5, 4, 3, 2, 1. All right, so let's see what we got here for the answers. Okay, decent mix here. Looks like more than half of you guys are currently using a CEM system. And there's actually about a quarter of you who are not doing peptide synthesis currently at the time. So I hope for those of you who currently got a system that you got something new and interesting and different to talk to you about today. And then for those of you who are currently not doing peptide synthesis, I'm hoping that you can learn quite a bit and get a lot out of today's presentation. So just to kind of get started, I want to talk a little bit about what can you synthesize with a microwave. And so first and foremost, be standard peptides. Now, when I say standard peptides, what I mean is I'm talking about peptides that just incorporate your standard, naturally occurring amino acids. But there's also a whole bunch of peptides that are modified that people are interested in, and there's been quite a bit of work in this area. And there's been several publications. If you do a simple literature search, you can see that many people have used microwaves to synthesize glycopeptides, phosphopeptides. And I'm going to touch on a few of these. But some of these, like dendrimers, for example, I'm not going to be able to get to today. But again, simple literature search, and you'll be able to find some examples of these. And then lastly, is the area of peptidomimetics. And this is something that we've become a little more interested in recently, especially because there's a lot of efforts toward working on peptidomimetics that actually are more like peptide and, say, peptoid conjugates. So something that you might be able to synthesize on these systems, but it's just new method development. So I'm going to touch on this a little bit too as well in the presentation. So what are the benefits of using microwave technology? Well, the first three here, these are the big ones that you'll always hear people talk about with microwave peptide synthesis in particular, is it's faster. So we've taken our synthesis time that normally would be a couple hours perhaps for a cycle to incorporate a single amino acid down to a matter of minutes. But also there's the benefits of improved purity. This is because we're doing it so fast, we can cut down on side reactions and also improved yields. Again, same kind of concept here where we're not having as many side reactions taking place, therefore we're getting better purity and yield. But really what distinguishes microwave technology from perhaps other types of energy processes would be it's a disruptive technology. Now what do I mean by this? What I'm getting to here is that it's got these 4 different characteristics. Rapid energy transfer. So basically, the microwave energy is rapidly absorbed by your solvent, the reagents, whatever is inside that mixture at the time, and it's basically instant on and instant off. So the second sort of option here is it's as soon as you turn the microwave on, there's microwave energy being applied at whatever power you've set it to, and then as soon as you turn it off, there's no more energy being applied. So it is very easy to control, very easy to put it in and put it in, then turn it off. It's a large amount of energy. The systems that we use typically deliver up to 300 watts. Now, typically for peptide synthesis, since we're operating usually in the lower temperature range, say maybe 70 degrees, 80 degrees, that you don't need quite as much power, but still it's quite a bit of energy that's available to us. And it can be selectively directed. And so I'll actually kind of come back to this in a little bit, but what I mean by this is that you can actually tailor the reagents and tailor your solvent, the conditions of the reaction, so that you can get more microwave energy into the reaction or into the reagents versus, say, the solvent. All right, so just to kind of give you just a quick update or quick idea of what I'm going to talk about today. Here we go. So I'm first going to go through the introduction of microwave synthesis. I want to go through a little bit of microwave theory. I promise I'm not going to bore you with lots and lots of physical chemistry, but I just want to give you sort of the CEM theory of why we would use microwave technology. I also want to give you a little bit of an explanation of the difference between microwave heating and conventional heating. And then I'll get to the good stuff. The stuff that I think you guys are probably most interested in is what can you use microwave technology to synthesize. So get into some of these applications and really talk a little bit more about the methods for doing some difficult peptide synthesis of modified peptides, and again, peptidomimetics, just because I think it's a new and interesting area. So what we have here is a schematic of a microwave. Now microwaves are made up of perpendicular electric and magnetic fields moving at the speed of light. And the frequency we use for our systems is 2450 megahertz. And the reason we select this is that there's actually 3 frequencies available to us from the FCC, and this is basically the frequency that's used in even your home microwaves. And so it's something we can easily take that same magnetrons that generate that microwave energy and incorporate it in our systems pretty easily. So this gives us a wavelength of about 12.2 centimeters. So you'll see that that's actually about the size of the microwave cavity itself, so that you basically have the size of a coffee cup, to give you an idea. And so again, at this frequency, this wavelength is good for our peptide synthesis. Reagents will absorb the microwave energy quite well. Now there's 2 mechanisms by which microwaves interact with a sample. And so those 2 mechanisms are called dipole rotation and ionic conduction. So what I have here is a little cartoon to show you what's happening during dipole rotation. So we have a sample of water, and we have our electric field here passing through our sample of water. Now what we know about water is that it has a dipole moment. And what's going to happen as this electric field passes through our sample, the dipole moment will begin to align with the electric field. Now it's not able to completely track the electric field, kind of as we've shown here, because every nanosecond another microwave is actually going to come through to the sample and disrupt this. So what happens then, it's going to begin to align and then realigns again with the next microwave coming through. And so what happens is then this will induce this wobble effect within these water molecules, and essentially that kinetic energy then is what gets translated into heat. Now ionic conduction that I mentioned is very similar. You can imagine that instead of water molecules here, I just now have ions in my solution. And it's the ions that begin to align themselves, moving within that solution, and then again getting that energy translated into heat. All right, so that's a microscopic view of what's happening when using microwaves to heat a sample. But let's take a step back and look more of a macroscopic view. And in doing so, also compare to thermal heating, conventional heating. So thermal heating relies on conductive heat. So I kind of have a little drawing over here to give you a very crude idea of what I'm talking about. And what we have is, so this is our hot plate. And what has to happen is, it could be an oil bath or a heating mantle. You understand, it's whatever this hot surface is. The surface of this must get hot first. It must heat up. So it needs energy to heat up the surface. The heat then transfers to the outside of our vessel, then through the vessel wall, so if it's a glass vessel, for example, through the glass to the surrounding solvents, and then slowly dissipates through the entire sample. So really, this is a big reason why when conventionally we're heating up a reaction, we want to make sure we use stirring to try and help dissipate that heat much faster and get to our higher temperature a little bit quicker. Now one thing to keep in mind though is once you turn off that hot plate, Some of you may have actually experienced this before. You turn off the hot plate, and this is actually still hot. So if you left your sample sitting there, there's still latent heat and latent energy going into the sample. Now, microwave heating is very different. So instead of heating up the outside of the vessel, the microwave energy will pass through the vessel wall. So the vessels that we use are, by and large, microwave transparent. So in the case of peptide synthesis, we're actually using a Teflon-based vessel. So the microwave energy will pass through the vessel wall, and it's going to directly interact with this sample. That's sort of what this crude, these little red dots are trying to show you, is that the reagents, the solvent, are absorbing the microwave energy. And what that can happen is that you can get sort of what we refer to as localized superheating. So you can imagine that if, say, in this sample, I've got my activator, so and I'm using, say, HBTU. So we know that has a counter ion, and I've mentioned that ions will absorb microwave energy. So if that counter ion is absorbing microwave energy, it's going to get a little bit hotter, perhaps, than the rest of the solvent around it. And of course, those little microscopic hot spots, because there's so much solvent around that, will rapidly dissipate that heat. But again, it's these little higher temperatures right at the site, perhaps, where the chemistry is taking place. So instead of at the counter ion, maybe at the peptide itself, this is where we're getting our enhancements with the microwave. Now, one of the nice things about the microwave, and I've sort of alluded to this before, is once you turn the microwave off, there's no more energy being applied. So the microwave itself, if you could touch it, it wouldn't be hot. There's no more energy there. Of course, you'll have the energy, the heat, latent heat in your sample, but that's it. So what does this look like then if we were to actually do kind of a slice through that vessel and compare what the temperature gradient would be inside the vessel of a conventionally heated sample versus a microwave heated sample? So that's what's shown here, is that with conventional heating, because again the heat comes from the outside and then has to dissipate in through the sample, it's much hotter on the outside of the sample, and where the bulk of your reagents are toward the center, it's much cooler. And again, then conversely with microwave, the opposite is true. In the center of the vessel, where the bulk of your reagents are, where the chemistry is taking place, you see that nice uniform temperature. It'd be a little bit cooler toward the outside of the vessel. So just one last comparison then of microwave versus thermal heating is to look at the heating rates. So what we've done here is we've taken our reaction mixture. This is a coupling reaction that we're doing here. And we're going to run this both in the microwave and also conventionally, so we're just using an oil bath. And our set temperature is 75, so that's what I have here with this dotted line to indicate the temperature we're trying to get to. And so you can see in the microwave method, it takes us about 1 minute to get up to temperature. But conventionally, it takes more than half of the reaction time to get up to that desired temperature. And also, just a side note, with the oil bath, we actually set the temperature even higher than the 75, so we could try to actually get it all the way up to 75 degrees in that 5 minutes. So what this means is that microwave energy is a very efficient way to heat your sample. So you could do this thermally, but you can see it doesn't quite get to temperature, so it's not going to be as effective as a method to heat as it would be with the microwave. All right, so now we're interested in peptides. Here we are. We want to know, okay, this is great. You've told us a lot about microwave versus thermal and microwave and conventional heating, but how is this going to, how does this change things for my peptides themselves? So when we look at a peptide, and we look at actually the calculated dipole moment, if we look at, compare the peptide bond itself and water, we find that the peptide bond is more than twice that of water. Now, why is that? Well, what we know about the peptide bond is that it exists in this resonance structure in about a 60-40 ratio. And you can see here this particular resonance structure is highly charged. And what that's going to do is it's going to generate significant dipole moment. And so again, this should then readily absorb microwave energy, because I talked about earlier that it's that dipole rotation is one of the mechanisms. So what does this look like when we're doing peptide synthesis? So here's a cartoon that we have here to show what might be happening when you're doing peptide synthesis. So here we have a peptide being synthesized on our resin. And what you'll see is that as we're getting through the synthesis, as we start extending the chain, we start to see protein or peptide chain aggregation. And so what's happening is that as the peptide aggregates, it makes the N-terminus here very inaccessible for either the deprotection reaction to remove the Fmoc, or it's inaccessible for the coupling reaction. But either way, this will cause deletions in our sequence, cause poor results. Now what happens when the microwave interacts with the sample is you have each of these peptide bonds. Now, the peptide bonds, all they're going to do is absorb that energy, and all it's going to do is induce molecular motion. And so basically you can sort of imagine that the peptide just begins to wiggle a little bit, and I'm actually sitting here wiggling even though you can't see me. But that's what's happening, and it helps to extend out our peptide chain, making that N-terminal more accessible. And then again, reducing the deletion sequences we'll see from poor deprotection or poor coupling. Okay. So just quickly, I wanted to talk just briefly what the optimized conditions are. This sort of summarizes a lot of work that we did at CEM to optimize the chemistry itself. And so when all the chemistry I'm going to talk about today is going to actually be Fmoc-based. You can do Bach chemistry in a microwave, but it would only be to accelerate the coupling reaction. You wouldn't want to do the Bach deprotection in the microwave since it's already a very fast step. So for the Fmoc removal, the deprotection step, we do a two-stage deprotection. So in the first stage, we get to about 45 degrees, and then we run that for 30 seconds. And then the second stage, we run up to 75, hold it there for 3 minutes. And the coupling reaction, we run for 5 minutes with our max temperature upward at 75 degrees. So in an automated sense, this gives us a cycle time of about 30 minutes, given all the washing that's required after the deprotection reactions after the coupling itself. Now I did want to make just one little note here is that we do measure the temperature actually internally inside the reaction mixture. So when we say that our temperature is 45 degrees or we say it's 75 degrees, it is indeed that temperature since we are directly measuring the temperature. So how does this compare then to conventional conditions? Well, so over here you'll see for deprotection, typically you'll see 5-minute and 10-minute deprotection cycle, and coupling can be maybe 30 minutes, sometimes 60 minutes, sometimes even longer, but say on average 60 minutes, given a cycle time of about 2 hours. So just to give you a comparison. Okay, so let's see if let's check in on you guys, see how everyone's doing out there. I have so another question for you. So what is your biggest concern about performing peptide synthesis in a microwave? This is often a question. People come to me and say, well, Grace, this is wonderful. You're saying how fast it is, but I'm worried about all these options. So are you worried about racemization? Are you worried about aspartimide formation? Do you want to use mild acid-sensitive resins, like a Chlorotrityl resin, for example, and you're worried about using that in a microwave? You use that for all of your syntheses. Or you're concerned about what's the microwave going to do to the peptide itself. Is it going to change somehow the physical and biological properties? I've often been asked, is it going to cook my peptide? So, and I'm asking what's your biggest concern. Maybe you're worried about all of these, but just let us know what's the biggest thing that you're worried about with running microwave peptide synthesis. So we'll give you guys a couple more seconds to get in some answers for us. But again, and don't be worried. I mean, you're not going to hurt my feelings by telling me that you were worried about running microwave peptide synthesis. So racemization, aspartimide formation, using acid-sensitive resins or sensitive resins in general, and the peptide parameters, or peptide, sorry, properties. So let's get those answers in. How about 5, 4, 3, 2, 1. All right. So I'm going to get these answers tallied up for me, and we'll get to that in just a second. So we've got here. Oh, all right. Well, it's a pretty even mix. Looks like about 30% of you guys are worried about aspartimide formation, and about 25% both the sensitive resins and then the properties of the peptide and about 19% the racemization. So pretty good even mix, and I appreciate the answers. So what I'm going to do is I'm going to talk a little bit about a couple of these, and some of them I won't be able to get to. For example, the last option there, the concerns about the physical and biological properties. For those of you who are concerned about that, I really encourage you to go to the literature. There's lots of examples where people have published basically synthesizing a peptide and then publishing the results of that those syntheses, and basically the biological properties are exactly the same. Okay, but to address some of these other concerns, I just wanted to quickly run through these. So here I want to talk about some of the potential issues, which we just mentioned, and what those solutions might be. Now, unfortunately, I could talk an entire 30 minutes about this, but we've published a paper kind of outlining all of this, and I do encourage you to go visit this reference. So when it comes to racemization, what we did is, we did what any good scientist will do. We visited the literature and we tried to see what options are available to us. We found that many people were using HOBT conventionally to limit racemization, and also that there's perhaps the benefit of efficiency. But what we find is that HOBT offers no benefit for coupling to improve the coupling efficiency or reducing racemization. So what we find is that just limiting our temperature to about 50 degrees for cysteine and histidine coupling only, because it's only during those couplings, the activated ester state, when the racemization takes place. If we limit it to 50 degrees, we can significantly limit the amount of racemization taking place. Now, when it comes to aspartimide formation, what we have found is that using 0.1 molar HOBT, you could also use Oximapure. I know that many people have concerns about the availability of HOBT. But you use this along with a 5% solution of piperazine, and that's a pretty effective solution for limiting the aspartimide formation. So lastly, just another potential side reaction that can take place is gamma-lactam formation. This is usually a problem when you're running synthesis where you have perhaps a difficult arginine coupling or slow arginine coupling. And what can happen is the arginine, the activated ester, can undergo lactam formation, and at that point it's unreactive to the coupling reaction. So what we've developed is a method that has a slow ramp of power, which makes it less of an issue in that particular case. Now, I should make a side note, and I forgot to mention this when I talked about racemization, that both the cysteine and histidine and also arginine, we actually have in the systems default methods. So default cycles are already in the system. So the system knows that if you're running a cysteine or histidine coupling, okay, we want to limit this to 50 degrees. So even if you forget, the system will remember for you. All right, so I just wanted to give a couple of examples then, kind of touching on this a little bit more. And one of the questions, or one of the options about the concerns was using acid-sensitive resins, like Chlorotrityl resin, for example. So I wanted to give just a brief example here. So here we're synthesizing the backbone of Octreotide. So it's short sequence, simple peptide. So we weren't too concerned about the synthesis quality here. But what we found when we synthesized this peptide on the Chlorotrityl resin at our normal temperatures, we found that we started to see a decrease in our yield. And the reason is because not only are these resins sensitive to acid, but they're also sensitive to temperature. And so what we find is that if we reduce the temperature for both the coupling and the deprotection, so you see here we're at 50 degrees for both coupling and deprotection, that seems to help limit this. Now also, in this particular case, Octreotide does not have an aspartic acid, so we didn't have to worry about aspartimide formation. But if you are running a sequence that is susceptible to aspartimide formation and using the Chlorotrityl resin, you do want to avoid the use of HOBT because it's also slightly acidic. So, and we could, if you have questions about that, we can talk about that at the end of the presentation, how you would deal with that. Okay, so what are the results here? So when we do the conventional synthesis, you see we get isolated yield 93%, crude purity is about 84%. So So our microwave method, you can see basically we get comparable results. And this is what we were hoping for. Really, we wanted to see that we aren't seeing a significant decrease in our yield. And 92%, we were pleased with that. Okay, so then what we wanted to do is come back and revisit this idea of aspartimide formation. Because many people associate aspartimide formation or believe that it's only aspartic acid followed by glycine. And then if they have any other aspartic acid, well, that shouldn't happen. But here's an example. This is the VIP, so vasoactive intestinal polypeptide, where there's actually not a DG, but we have a DA and a DN. And these are both actually susceptible to the aspartimide formation. Now, what we also wanted to do is study, again, revisit this idea of adding the HOBT and the deprotect. So some people wanted to see some of the examples of this. So what we did here in this study, and I know it's a lot of information here, but really the point is here in this deprotection. So first, we ran the synthesis in the microwave with no HOBT in our deprotect. And then we ran it with the HOBT. Now in both cases, we are using 5% piperazine. And here's our conventional comparison. So our microwave method took us about half the time. Well, what does that look like in the results? I apologize for pushing that too far. So here, in the first example, this is without HOBT. You can see that we have 27% is our crude purity. And you can see significant formation of the aspartimide side product. Now, since we are using piperazine, it does come up basically as a nice clean peak. So simply just adding that 0.1 molar HOBT, you see we can almost essentially suppress the aspartimide side product, improving the purity up to about 80%. Now just the comparison to the conventional method, you can see here we get about 45% crude purity of the sequence. So not quite as clean as we get here with the microwave, and again we do this in half the time. So then just to finish up on on standard peptides, I did want to quickly just talk about microwave deprotection and really the importance of this step. So in this particular sequence, we synthesized this peptide using room temperature deprotection and using only the microwave for the coupling step. We only get about 33%. So here's our target, and you can see all these peaks here in the HPLC. This is due to deletion sequences. And what we find is it's because of inefficient Fmoc removal. So simply by just running the microwave in our standard deprotection conditions, so 30 seconds and 3 minutes, we now see we've essentially eliminated all of those deletion products and get about 88% crude purity of that peptide. All right, so I'm going to switch and talk about some modified peptides. I mentioned I was going to get into just a few of these examples. So this particular example is synthesis of a head-to-tail peptide cyclization. I know there's lots of examples out there of cyclized peptide. This is just one mechanism by which you can cyclize. So what we did here is we wanted to use an orthogonally protected glutamic acid, and we selected the DMAB protected glutamic acid. So in these first two steps here, we're just basically doing our linear synthesis. These are our standard conditions, nothing out of the ordinary here. And basically we can generate our peptide quite cleanly for our linear sequence. So our next step in the process was to remove the DMAB. This is done with 5% hydrazine. So what we did is we did basically a double deprotection, so 2 times for 3 minutes, 75 degrees. And I guess I probably should note that when I say 3 minutes, 75, this is actually 3 minutes total time, 75 being our maximum temperature. And so this comes basically quantitative. We can remove that DMAB and get nice, very cleanly our linear peptide, where now we have access to our carboxylic acid. We're still on the resin to be able to do our cyclization. So for the cyclization, we explored a variety of different conditions, and what we found is that DIC HOBT worked the best for this cyclization. Also what we found is that we really needed to do this 3 times at 10 minutes. So doing it only 2 times at 10 minutes or perhaps for 30 minutes just straight didn't quite give us as good of results. So 3 times 10 minutes to do the cyclization, and then once we've cleaved from the resin, we get our desired peptide. and about 77% crude purity. But the key point here is we're able to reduce that cyclization time from an 18-hour process, so from the DMAB deprotection itself through the cyclization, and we were able to do that in less than 1 hour. And what's really neat is we were able to do this completely automated as well. So we didn't have to stop the system to be able to introduce new reagents. We just were able to do this straight through and get this in good high crude purity. So here's another just different example for a modified peptide. This here is an example where we're using the Aib residue. I'm sure many of you are familiar with this particular derivative. So it's the amino isobutyric acid. So what makes this particular residue a little more challenging than your standard, say, alanine, is that you've got this additional methyl group, and that is causing steric hindrance and can help to slow down the coupling reaction, and sometimes, in many cases, almost completely prevent a subsequent coupling from taking place. And so we wanted to look into just a simple synthesis where we have 2 Aib residues, and actually these are one right after another. So it's a little bit of a challenge for this synthesis. So we did both a conventional microwave comparison, and actually this table is essentially the optimized conditions. We did quite a bit of study here. So what we found is that for the coupling reaction, we used HCTU as an alternative for the activator, and we used a mixed solvent system for our Aib residues. So I mentioned earlier the fact that you can tune the synthesis conditions to try and take advantage of the microwave energy. So when we switched to using dichloromethane as part of this mixture, part of our goal was to allow more microwave energy to be applied. And that's because dichloromethane is not quite as microwave absorbing as just DMF. Now we have a secondary effect here also by using dichloromethane. Because its boiling point is so low, we're likely to have a concentration effect where basically some of that dichloromethane will actually evaporate through the process because it's so low boiling. So what we found is that we did double coupling for our Aib residues. We also did kick the temperature up to about 95 degrees. We see we get pretty good purity. And here's our conventional comparison, just using essentially the same conditions, but conventionally. So our synthesis time, about a quarter shorter with the microwave, but really the key is to look at the actual results. So here's our conventional synthesis. So here's our product, and we get that in about 30%. But you can see here significant Aib deletion. So that one of those Aib residues is not coupling to completion. Now here in the microwave, now you can see, okay, we were able to get our main peak here is now our product, which is what we want to see. We do still see a little bit of Aib deletion, but you can see our major target, our major product is our target. And again, quarter of the time to get to that result. So I mentioned that there are other methods for doing cyclization. So this is an interesting result. This actually comes out of Monash University in Australia, where they're looking to synthesize chronotoxin analogs, but they're using basically a dicarba bridge as a disulfide mimic, essentially. And what they're doing here is using metathesis to form these dicarba bridges. So they synthesize the linear sequence with these prenyl groups, and then you've got terminal alkenes. So first they subject this to a metathesis reaction using Grubb's second-generation catalyst. So after about 2 hours at 100 degrees, basically they get clean formation of the metathesis product. And again, none of the prenyl groups are actually reacting in this particular metathesis. So it's selective metathesis. Hydrogenation with Wilkinson's catalyst then gives the saturated compound. Then the prenyl groups are activated using cis-2-butene, and then a subsequent metathesis reaction, again, same conditions with Grubb's second-generation catalyst, 2 hours in the microwave, 100 degrees, gives the desired metathesis product. And this can be taken on and hydrogenated as well. But really the point here is that trying to run this chemistry at reflux in dichloromethane for 40 hours, almost 2 days, gave no conversion to desired product. So we're able to take advantage of one of the other characteristics with microwave, and this is a different example. This is not doing this perhaps in an automated synthesizer, but in a different type of system. Okay, so I did promise I would get to peptidomimetics, so just quickly, in the last couple of minutes here, I want to give you a couple of examples. So here we're going to go through the synthesis of peptoid. So peptoid synthesis, if you're not familiar, this is an example of the submonomer approach. And what essentially you do here, instead of doing a deprotection and a coupling like we do in our Fmoc synthesis, for example, the first step is to do an acylation and then do a nucleophilic displacement with an amine. And so in this particular case, we're just synthesizing all using the same methoxypropylamine, but you can imagine that any amine can be used here. So here's our conventional conditions. So both the acylation and displacement, we ran these at room temperature for 30 minutes. And for our microwave methods, we ran them at 75 for 5 minutes. So you can see here, synthesis is about less than half the time, but the results are a pretty significant difference here. So conventionally, here's our target. And you can see iterative examples of each deletion of each of those monomers through the synthesis. And we've actually repeated this a couple times to really show that indeed this is the results we get. With the microwave, very cleanly we get to 94% crude purity of this particular peptoid. So pretty exciting results. All right, so the last peptidomimetic I wanted to talk to you about is a PNA. So for those of you who are not familiar, PNAs are DNA mimics, but they have a pseudopeptide backbone. So you've got these repeating aminoethylglycine units, and essentially you've got coming off of this particular nitrogen, you've got through an amide bond the corresponding bases for DNA. And what's really interesting is that these form really stable base pairing with DNA or RNA, and actually even stronger than DNA base pairing, for example. So it's pretty stable. And what's interesting also is that due to the nature of the structure, these PNAs are resistant to nucleases and proteases. So this has been a really exciting area of research. So this group here at the MRC in the UK, they are synthesizing this particular PNA, which has 23 PNA monomers, flanked by just your standard, we've got lysine here on the C terminus and a cysteine and lysine on the N terminus. So what they find is that for the deprotection for these C-terminal lysine, they can use the standard microwave conditions. But once the PNA monomers are incorporated, essentially they run all this at room temperature to avoid potential intermolecular cyclization. The coupling reaction was done with PIBOP. So for the standard amino acids, using pretty much standard conditions for 5 minutes. However, the PNA monomers required a little bit longer time, about 30 minutes for the coupling. So what does this look like then? So this is their MALDI-TOF mass spec analysis. So here's the results from the standard synthesis. You can see pretty much very small amounts, if at all, the desired peptide. And here's the microwave method. So here you can see much more of that desired sequence. And what they find is that the microwave synthesis is 2.5 times faster with a 10-fold increase in the yield of the desired PNA peptide. Okay, so just to sort of sum up what I've talked to you about today, I talked to you about how microwave can speed up the synthesis but also improve the synthesis quality, and talked to you about how you can use microwave energy for both steps in the Fmoc process, so the deprotection and the coupling. Briefly mentioned how side reactions are easily controlled and gave you some examples of how to deal with any of those issues. And then gave you some different examples of some difficult peptides, some modified sequences, and then some peptidomimetics as well. You know, again, this was a very brief overview of some different examples, but I just wanted to touch on a few different areas. So with that, I would like to thank you all for your attention, and I'd be happy to entertain any questions. And I do have my contact information, so if you have a question that you'd like a little more detail about, you certainly are more than welcome to send me an email as well. So with that, please enter your questions, and again, I thank you all for attending.
Thank you, Grace, very much. I noticed that it's remarkable how much microwave peptide synthesis can improve purities and decrease the time it takes to make a peptide. But is it any more difficult to operate than the conventional synthesizer?
Actually, really it's not that much more difficult. The system is designed very much like any other conventional synthesizer. It's a software that allows you to program a sequence, and I mentioned before the fact that we have default methods in there, so it's really quite easy to run the peptide synthesis like you would be running any standard synthesizer.
Right. We have some questions here. We have one from Venkata. He'd like to know if you have any suggestions for resin choice for C-terminus cysteine acid peptides.
Typically, when we run C-terminal cysteine, we would suggest using the Chlorotrityl resin. We've had the most success there with the C-terminal acid cysteine. Certainly, if you're running an amide, you could use any sort of amide resin.
Wonderful. And Erica would like to know if you could talk about the advantages of HCTU over HATU and HBTU.
Typically what we find is that HCTU might give you slight advantage over HBTU. We only typically use HATU when we really have something particularly difficult. A good example is when we synthesize N-methylated peptides. We find that those couplings can be a little bit more difficult, and so that's when HATU really comes in handy. But it's usually, that's sort of our go-to if we really can't get something to work.
Okay. Also, we have a follow-up on the cysteine question. What protection on cysteine chlorotrityl resin do you suggest?
Typically, we use a trityl-protected cysteine.
Awesome. Do you have any suggestions for intramolecular cyclization of tetrapeptide to form 12-membered rings?
That's a good question. That's actually not something we've actually tried. So I might start with the conditions I talked about with using DIC, and then might have to tweak the conditions from there. I'm just without having tried, I don't really know much more than that.
Oh, okay. Have you all done a synthesis of the larger peptide of 35 plus amino acids comparing convention and microwave methods?
Yes, we certainly have. Beta amyloid is a perfect example where we've done synthesis conventional versus microwave. The microwave method, you get, I think, about 80% crude purity. Conventional comparison, depending on what conditions you use, are much, much lower.
Oh, another question here. It looks like your reaction monitoring plots, the desired product shows up at a peak at a particular time. This implies that the reaction goes all at once rather than happening gradually as heat is added. Why do you observe this phenomena of conversion to the product all at once? So when I show the results at the end, that's actually just our synthesis at the HPLC. It's not really tracking the synthesis as it's running. We do use UV monitoring to track our deprotection, but again, that's after the reaction. So none of this is actually real-time monitoring inside the reaction mixture. Okay. Why is HBOT added to piperidine? Is it required?
It's good to add HOVT to your deprotection if your sequence is susceptible to aspartimide formation. It's not required, but if you do see aspartimide formation taking place, you might want to add the HOVT. Again, I mentioned before, Oxmopure also will work, but what it does in the deprotection, and this is just theory that has been put out there, is it helps to buffer the solution, making the piperidine not quite as basic and not allowing that aspartimide formation to take place.
Can you use an HOVT hydrate for that deprotection?
Absolutely.
Okay. What is the best protection group that you've seen for an SS bond?
We've used the ACM protected cysteine to do the disulfide
or protect for the disulfide bond. It depends on when you want to do the disulfide formation. If you want to do it on resin, ACM works well. We've actually done them off when you've cleaved off the resin as well, so you could use just standard Trittle in those cases.
Oh, okay. We have a Liberty 1 peptide synthesizer user here, Naomi, who would like to know how she would mix the solvents to use DCM, DMF for an Aib coupling. Currently, her system only delivers DMF.
Well, so that, when we did that mixed solvent system, it's what we use to dissolve the amino acid. So if I was using the Aib residue, I would mix it up. If I was making 10 ml solution, it would be 5 ml DMF, 5 ml of DCM.
Okay. And how do power changes in the Liberty 1 affect the long peptide chains?
We don't do much. When we've set our power settings, usually we use them for the entire synthesis, so we don't really find that we need to change them. We sometimes, for different scales, will change the amount of power we add, but that's not something we found we had a need to change.
Have you ever used alkyne or azide on the side chain in a microwave synthesis, or did you see side reactions in that?
That's actually an ongoing project that we have going on. Our initial results, I would say, we don't see much with the side reaction, but we haven't done thorough studies where we've had them, especially toward the beginning of the sequence, and done the entire synthesis. But the initial results show that there's no side reactions.
If we use a DCM in Liberty, are there any pressure issues at the cysteine coupling peptide chain?
Pressure issues by going above the boiling point, I'm assuming, is the question. The vessel is not pressurized, so it actually has a vent. So if essentially if you're running with dichloromethane, the vapor will escape through the vent. So there's no concerns about the pressure, if that's what you're asking.
Okay, we have a couple of hard system questions here. How does the UV monitor feedback work?
So the UV monitor basically will essentially measure the UV absorbance of the deprotect, basically the waste from the deprotect after each step. So after the 30-second, it'll drain, measure the UV absorbance, and then also we'll measure the UV absorbance after the second deprotection.
Okay, and what is the largest volume you can run in the microwave?
Well, the largest vessel that we have for our Liberty systems is a 125 milliliter vessel. We don't suggest going above about half the volume of that, so you're looking at about 60 some odd milliliters. To give you an idea on scale, typically, because that's often how we talk about it, 3 millimole can be done. We've seen cases where people have actually pushed it up to 5 millimole.
Okay. And Rajesh would like to know how microwave heating compares to infrared.
Well, essentially, the infrared is going to be very similar to the thermal heating that I was talking about. Essentially, you're going to see the same kind of results. It's essentially going to heat from the outside rather than heating from the inside, and you're going to have higher temperature on the outside versus on the inside.
Okay. Naomi has another question. When using HOBT in the deprotect, we see a UV trace because of the UV activeness of HOBT. Is there a way around this?
Yes, good question. We get asked that many times. So if you're running, if you're trying to use the UV monitor and you want to add HOBT, or you have a problem with aspartimide formation, we suggest actually looking at a different aspartic acid protecting group. There is an OMPE protecting group for the aspartic acid that works quite well. It is a little bit more expensive, I'll admit that, but it works quite well and allows you to still use the UV monitor for your deprotection reactions.
Okay, that's good to know. Are fluorescein fluorophore peptide conjugations affected negatively by microwave energy?
Not in our experience. We've not done much with that. We've done a few examples. Actually, we've worked with a couple of customers on that, and we've not seen any negative results there.
Oh, awesome. What is the maximum peptide length that you can make in a microwave synthesizer?
Well, that's still yet, I think, to be determined. There's a couple publications out there. One, they've done the synthesis of 111 amino acids, and there's another one that's 109. So I think the competition is still on to see what is the maximum length that you can synthesize.
Oh, well, we look forward to seeing how long that can go. Are there any peptides that you don't think benefit from using microwave energy to drive the reaction?
We've synthesized hundreds, probably at this point thousands of peptides in our lab, and we've not seen any examples where you wouldn't want to use the microwave. Now, I will say there are some cases where the microwave will give you comparable results to what you see conventionally, but keep in mind that that's still going to be faster than you see with conventional conditions, and then again, in many cases, you'll actually see improved results. So I see no reason why not to use the microwave.
Oh, good. Another hardware question, this one from Trudy. How does the one-shot option work?
Okay, so the one-shot option, what that allows you to do is basically add everything out of the reaction, or sorry, out of the amino acid bottle. So if you wanted to put only 1 milliliter into the bottle, you put 1 milliliter in, and then the one-shot will add basically until all of that reagent is into the reaction mixture. It works particularly well for small-scale synthesis.
Well, Grace, thank you very much for your time today, and we really appreciate you coming in and explaining all of this. And we really appreciate all of you out there in the audience joining us today. If you have any other questions, please feel free to contact Grace at grace.gagne@cem.com or give us a call. We'd be happy to talk to you. We hope you have a wonderful day, and thank you very much.